Good evening, everyone. So, my talk is on volcanic lightning, which is something that I got into accidentally. I went to school and trained to be a seismologist, so I learned all about earthquakes. And then I was interested in volcanoes, so I did most of my research on volcanoes. Well, then one thing we discovered one time that in 1992, a volcano called Mount Spur erupted in Alaska, and a series of spikes, which we first interpreted as noise spikes, showed up on our data. Now, normally, if you're a seismologist, you don't want lightning because it makes spikes, it makes noise from a seismologist's point of view. But we eventually discovered that our seismic data had actually recorded a pretty good sequence of the lightning at Mount Spur. So had a summer intern work on the project and tallied it up and then ended up writing a paper on volcanic lightning. Now here's a slide showing volcanic lightning. This is taken by one of my colleagues named Harold Edens from New Mexico Tech. This was an experiment last year in Sakurajima Volcano in Japan. And one thing about volcanic lightning, it's very photogenic. So I've seen lots of covers of books. So lightning at volcanoes is actually quite common. It showed up in over 150 volcanoes and well over 400 eruptions based on a literature compilation. So it's quite common. It took a long time for it to be appreciated as something more than a curiosity. It turns out that lightning tells us some things about electrification in the plume, and we can actually use it to confirm that an eruption producing ash is underway. So here's a figure showing there's different kinds of lightning. In looking at data systematically and data from a variety of instruments as well as direct observations, we see that lightning has a couple of different types. On the lower left, when an eruption first starts, there's little tiny lightning flashes. They're very short. It's a couple microseconds long. A little vent, we call them vent discharges. It's not like a full-fledged lightning flash, but it's little disorganized individual like sparkles or flashes. Some of them are maybe tens of meters long. The second one over in the middle, we call near vent lightning. So near vent lightning occurs when the ash column first starts to go up, when it gets up maybe a kilometer or two, and the lightning has a scale length now, instead of a few tens of meters, the scale length is hundreds of meters, maybe up to about a kilometer. And then the third one on the right there, when you get a huge plume developing, especially when it gets up about 10 kilometers, then you get large-scale lightning, which is very much like lightning from thunderstorms. So we get the small-scale lightning. The vent discharges only seem to happen at volcanoes. The near-vent lightning is from electrical processes in the small-scale plume, but not involving ice. The plume lightning, when you get a big, tall plume, the top of it is high enough that it's below freezing. So then what happens is you start getting ice formed. And this has been, some people have called this a dirty thunderstorm. So ice, it turns out, Michael Faraday did some of the original experiments to see the electrical properties of various substances. It turns out ice is the most electrical positive substance known. It really likes to shed electrons and end up with a net positive charge. So that's why ordinary thunderstorms that we get very commonly here in Florida are very efficient. Ice at the top of the cloud is little particles of ice have a positive charge, the water droplets below have a negative charge, and you have a big dipole in the sky. And when the electric field gets strong enough, you get electrical breakdown through the air, and that's what we see as a lightning flash. So the same thing happens in the plumes, and so we call that plume lightning to distinguish it from the other types. But otherwise, if you just looked at the individual lightning flashes, it's very much like a thunderstorm. So what are these processes? Where do the charges come from? So there's two main ones that happen. One is called fractal emission. Scientists love to use big words. Fractal emission. So frac comes from fracture. So basically, when you take particles and break them, invariably, some of the electrons are loosely held and some tightly held. Invariably, one of the particles will end up with a slight positive charge, and the other will end up with a negative charge, as shown in the picture there. And you sometimes get little ions splitting off. So electrons are not uniformly held by different substances. In fact, this is why I mentioned ice before. Ice likes to be positive. It likes to get rid of electrons on the surface. So you take any old substance like ash particles and you start breaking them, and you get a division of the charge based on surface properties. Now, once the particles are formed, we think this happens first, because when a volcanic eruption happens, the magma gets blown apart by the dissolved gases in it. So once the particles exist, a second process takes place. This is called tribocharging or triboelectrification. This is when particles collide with each other. So the upper part shows the two particles coming together. They collide, they interact. Again, some of the electrons are tightly held, others are loosely held, and you get a small charge transfer. So when after the collision, one of the particles will be positively charged and the other will be negatively charged. So tribocharging and fractal emission are the two main processes that cause the charge. And then convection, heat, hoists the particles up into the air. Then the other thing that we need is gravitational settling. So gravitational settling, all that means is the fine particles rise up and the larger ones fall because of gravity. So you get sorting in the column. As you stand back and wait a few minutes, the top of the column will be mostly small particles, the bottom will be mostly larger ones. So then using this as a little bit of a framework, now we can look at some more cool pictures and comment on the different kinds of lightning. So this is a volcano called Colima in Mexico. The column there is a few kilometers high. This is probably the near vent lightning. The scale length is a little less than a kilometer. You can see the lava on the surface of the mountain rolling down the hill. So this is no ice in this eruption. This is all hot material, but probably the fractal emission and tribocharging are the most dominant features there. The second one, this is a wild picture. This is a big eruption of Mount Etna, and it almost looks diabolical. Okay, so now what do we see? We see the top of the mountain's about 3,000 meters up, and the plume is going way up until it hits the tropopause or troposphere, and you get the lateral spreading of the cloud. That's high enough up that you start to get ice. So if you're getting ice, now we're switching over to plume lightning. Now this is a weird picture because what you see is lightning starting at the base of that of the tropopause and propagating down like devil's pitchforks. So that's probably positive charge, because if you got a lot of ice particles, it's invariably going to be net positive charge. The positive charge is then trying to go down and neutralize with negative charges below. So that's one peculiar type of the plume lightning. Normally, plume lightning is bigger scale length. It would be several kilometers long, and it would look like thunderstorm lightning. But it's a cool picture. And then here's another one from Sakurajima. Now here the scale is from about the middle of the picture over to the right is about a couple of 100 meters. So this is the larger flashes you see are near vent lightning, and then you see a bunch of little tiny little flickers, little bits of lightning that are only 10 meters or so long. This is probably the vent discharges that we've seen. So we had an experiment here last year, 2015 and 2016. We set up instruments to record the lightning, 10 specialized instruments that are designed to record lightning. We also use seismometers and infrasound sensors, various types of cameras. We wanted to get a full picture of the lightning. And what we were after particularly, this volcano, Sakurajima in Japan, is very good at making lots of eruptions with lightning. And what's been understudied so far, the big obvious lightning, the plume lightning, there's lots of photographs and it shows up on distant systems. The little tiny fine scale lightning only shows up if you have the right kind of instrumentations to catch it. So that's what we've been studying, trying to understand the source processes of that. And back to the beginning again. This is the one we started with. Now that we know a little bit more about it, this is probably near vent lightning. The scale length is several hundred meters. It's a little bit of a time exposure. You can see the red streaks there are ballistics coming out of the eruption. So lightning at volcanoes does a couple things for us. It tells us about electrical properties in the plume, and that information is complementary to particle size, composition, gases, other things. It tells us about the activity of the plume as a whole. Electric charges are one of the things that cause particles to clump together. Sometimes it's observed there's things called accretionary lapilli. Little particles clump together and they make larger particles and they settle out faster. And electrical processes are one of the things responsible for that. Let's see. From a monitoring standpoint, if you get the combination of a signal that shows up in your seismometer, so the ground is shaking, and infrasound, so you get a signal traveling through the air, showing up in microphones, and lightning, that's the telltale signature that you have ash, volcanic ash. This is not ash in your fireplace. It's a textural term for volcanologists. It means tiny little particles. And anecdotally, over the years, it's been shown that the more fine ash, very small particles in a plume, the more lightning you have. So that's one of the things that the fine particles are the ones that cause problems with aircraft. So in remote areas, the combination of seismic signal, infrasound signal, and lightning would be good evidence that there's an ash cloud in place and provide part of a warning system for ash-producing eruptions in remote areas. So that's probably a good place to stop, and you don't know how they're working it for questions, but I assume we're taking questions?
So just tell me what kind of questions you do your best.
All right. If anyone has a question, I'll do my best. Well, it's not so much the charges exist, it's a question of redistributing them. If all the particles are neutral, you would think that may happen some of the time, but experiments have shown. But people have, like, one time on a summer job, I was doing sandblasting. And so sandblasting, you have a nozzle that shoots sand particles at high velocity. You had to wear these giant rubber gloves because it generated so much static electricity. So the thing that seems to be dominant is how tightly held the electrons are. And as soon as they get separated, then you end up with a net charge on the particle left behind. Somewhere, there ought to be a redistribution to make some of the particles electrically neutral. But the thermodynamics favor the separation of charge in a high energy environment. Okay, the question is, how big is the lightning and how does it compare to a lightning storm? I'm going to go back to that schematic that I showed you earlier. Okay, the plume lightning, which is when the plume is 10 kilometers, it's almost indistinguishable. The duration of individual flashes is up to about a half a second or so, which is very much like ordinary thunderstorms. The scale length on the order of 10 kilometers is very similar to ordinary lightning. So in fact, some of the big volcanic eruptions have produced thousands, up to about 10,000 lightning flashes, which is the same kind of numbers you get with big thunderstorms in the Midwest. The small scale lightning, the near vent lightning and the vent discharges are much shorter scale length, much faster, and they seem to be only restricted to the volcanoes. Yes? The question is there always lightning? No. The one we went to, Sakurajima, we sat there watching it for about 2 weeks straight. And I don't have an exact percentage. A fairly high percentage of them had that smallest level activity, which was difficult to observe. We caught it on our instruments. The larger ones are the ones that had the more spectacular and visible lightning. So it's a subset. This is one of the questions we're trying to answer is, what exactly are the conditions that you need to have lightning? Because if you're going to say there's lightning, therefore there's an eruption of a certain size, you need to have some numbers to back it up. You need to know how big is it when you don't have lightning, and what's the smallest one that does have lightning, and how much overlap there is between there. But not all of them. Yes? Yeah, Sonia Banky was a postdoc at USF in 2014, 2015. In fact, she's one of the co-PIs on this project. Yeah, and so one paper that we worked on together was looking at the different lightning recording systems and what they record. The big lightning flashes will show up at regional distances, and they're easy to pick out. The small scale ones are the ones that are hard to say. So I'm not aware of any blanket answer. With the volcano in Alaska called Redoubt, what we saw was if the plume was less than 10 kilometers and the signal on a particular infrasound was less than 38 pascals, then you'd have 100 lightning flashes or fewer. If it was more than 10 kilometers and higher than 38 pascals, immediately you jumped up into the thousands of flashes. So there seem to be thresholds that work at different places. The right combination of explosivity and height of the column, which is probably ice, together will make sure there's lightning. But a lot of volcanoes have little eruptions, and they don't always have lightning.
So is that static repulsion?
Is that
static repulsion?
She's asking if it's various static electricity. Yeah, I think the tribocharging, the particle collisions are the most common mechanism for the small scale eruptions. But you still have to have sufficient amount of charge to get up to the point where you get dielectric breakdown of the air. Good question. We think it's most likely the plume lightning. So I should say something about that. It was a remote area of Alaska where, the question was whether the lightning at Mount Spur in Alaska that showed up on the seismometers was, what kind of lightning was that? And I think it was the plume lightning rather than these small scale lightnings. The technicians were kind of in a hurry, and normally you bury the seismometer about a half a meter down to keep the noise level low, and then you also bury the cable. they didn't have time to bury the cable, so it was lying on the ground surface. So then what was happening, a wire lying on the ground surface is like an antenna. So the lightning produces a wideband electrical signal, and it was coupling directly into the electronics, into the cable lying on the ground, in between the seismometer and the electronics package. So we deduced that from looking at a number of observations. That would not typically be the case. Normally, electronic technicians are very unhappy to find out lightning is showing up on other equipment. They then feel they have done a bad job of grounding or shielding or other things that are done. So it's kind of an accidental thing. Others? All right. Thank you.
Okay, we're going to take a quick break, so make sure you refill those beers.